Okay, I think it's time. So let us start. So in the last lecture, we saw Bayesian inference, maximum likelihood estimation, and maximum a posteriori estimate in the context of a very small example, which is the coin tossing example. And we saw that how the results are different, under what situation the results become same, like MAP and MLE, we saw one case for that. And we also kind of saw that why Bayesian is the way to go, how it helps us, how the one smoothing thing I also discussed last time. And that example was supposed to motivate for what is coming in the lecture. Okay. So, today we are going to start with prior modeling, and the hope is that we will be covering most of the things of prior modeling today. Maybe a small portion will remain, which we will cover in the next lecture. But the hope is that most of the things on prior modeling will be done by today, and the reason is that, as you will see, that in prior modeling it is a evolving field. There are research that is happening right now, and so we will only be discussing the things that are kind of well established, and we will not talking about things that is evolving. The idea is that the established part of the is what forms your fundamental. Other things, if you want to explore, you can explore on your own. Okay. So that is the idea, and in prior modeling we will talk about different aspects of prior modeling, what you can do and what you cannot do. Okay. So with that background, let us quickly recap what we did last time. Basically the same recap. We did Bayesian inference, right? And in Bayesian inference, by now you already know that if I am talking about Bayesian inference, in Bayesian inference I will be talking about this thing, right, the Bayes law, but I will write it in the proportional form. So this is how it will look, right. We have the posterior on the left hand side, which is proportional to the product of prior and likelihood. And as I told last time also, that this formula is what this course is all about. How to use this formula in different contexts, what will be P of theta, what will be P of d given theta, and how to find out probability of theta given d, and so on and so forth. So this course is about this formula. Okay. Bayesian machine learning, Bayesian statistics, Bayesian inference is about this formula. Okay. And now clearly one important component is P of theta, there is no doubt about that. And last time we saw that what a strong prior can do, if I increase the strength of the beta distribution, we saw that that can dominate even the likelihood if I increase it unreasonably. So to model P of theta appropriately is essential to get the posterior correct, to get a meaningful posterior. If you take some unreasonable P of theta, in that case your posterior will be having some influence of that P of theta, the prior, and your posterior might not be a good posterior. Okay. So one of the key things is modeling P of theta. Okay. So one key aspect is to model the prior, which is nothing but my P of theta. Okay. And what is the goal of modeling prior? The goal of modeling prior is that whatever information is available to you should be reflected in the prior you are selecting. I mean, in the ideal world, that is the goal, that whatever information, prior information is available to you, that should get reflected in P of theta. That is what prior is. So ideally our prior knowledge should be reflected should get reflected in our choice of P of theta. So, this means that if I know, let us for example, that theta is supposed to be I do not know non-negative, then I should select a P theta ideally that is also non-negative, that will always give positive value. If I know that, that should be reflected in P of theta, right. If I know that that theta is supposed to be shift invariant, and in many cases we do encounter problems which are shift invariant. So, for example, classifying a cat in an image, whether the image, the cat is on the left side of the image or the right hand side of the image, your results would not change. So, that is a shift invariant example. Okay. So, then there can be rotational invariance, that even if you rotate the image, the outputs would not change. Again, the cat example holds here also, but rotational invariance is very dangerous. One example is if there is a 6, if you rotate it, it will become 9. So, all these things are to be modeled properly. If you take some wrong information, let us say you are modeling 6 and you are using rotational invariance, your prior is wrong. So, your posterior will also be wrong in some sense, right. And like that there can be other things also, right. So, what I was saying is that we are trying to model the prior, and the prior model, the model of the prior should reflect our knowledge about the system or theta in this case before we have observed any data in the ideal world. Remember, I am using the ideal world again and again, because you will realize that we will violate these things. Whatever I am saying will be violated. So, that is why I am repeating the thing ideal world. Okay. So, for example, let us take the coin tossing example, right, from last time. What was our prior? Beta distribution on theta. What was theta? Probability of getting head. Now, suppose my prior belief is that this theta or the coin is unbiased. Let us say my prior belief is that the coin is unbiased. That is a possible prior belief, right, that the coin is unbiased. So, in that case, forget about the beta distribution, but what do you think should be my prior? See, if you are very certain about that, then your prior should be a delta function at theta equal to 0.5. That means it is 1 there, everywhere it is 0, right. So, it should peak at theta equal to 0.5, everywhere else it should go to 0. If my belief is very strong that my coin is unbiased, but that is problematic, probably you do not want to be so strong. So, what can be a soft prior that enforces that, okay, this holds? A soft prior can be something where the beta peaks at 0.5 and then maybe it goes down to 0 at or close to 0 at both ends. So, you can think of it. So, for that you need to find out the parameters of beta distribution such that that holds.
Sir, why it's like this only?
No, it can, because it's you will, if you take it to the right, that means you are saying that the probability of getting head is more than getting tail. If it is skewed towards the other side, that means you are saying probability of tail is more than probability of head. But you have assumed that, or your prior belief is that the probability of its unbiased coin.
Then we will take 0.4.
So, that is a very strong prior. So, what you will, and with that then there is no problem to solve, it is a delta function. So, what you will want is, if you have to do Bayesian, that your belief is that it is unbiased, but your belief, you are flexible in your belief. So, at 0.5 it should peak and then it should be somewhere, and the flatness, the variance should be a function of how strong is your belief. If your belief is very strong, this should shrink. If you are flexible, then this should be flat.
So, if you talk about MLE,
Not MLE, your prior. I am talking about only prior. There is no MLE here. I am talking about your prior belief about a coin being unbiased.
so like there is no prior in MLE, so we can say that there will be a
but we are not talking about MLE. MLE is flawed, that we have already discussed. Today we are talking about Bayesian inference. In MLE there is no prior. Today's topic, since you came late, is about prior modeling. So that is an invalid question, because we are talking about prior modeling. In MLE there is no prior, right. So we are talking about prior modeling, and what I said was that, so for example, if my prior belief is that the coin is unbiased, then one option is to model P of theta, which is my prior, as a direct delta function that peaks at theta equal to 0.5, right. And this means there is no uncertainty, because how will it look? This distribution will look something like there is a peak here at 0.5, everywhere else it is 0. This means there is no uncertainty in your prior. This means you are absolutely certain that it is theta equal to 0.5, even before observing data. And in such case, it is very unlikely your data will be able to change your belief. If I am 100% certain about something, no matter how much data I get, will I change my belief? Because I am 100% certain, it is very unlikely, right. So this is a very strong prior, right, and you probably do not want to use such a strong prior in a practical scenario, right. It is like being extremely overconfident, and we know being overconfident is not a good thing, right. So another option is a softer alternative is to model it as some distribution, okay, that will peak at theta equal to 0.5, but will fall down and goes to 0 probably at 1 and 0, right. So that a distribution that peaks at theta equal to 0.5 and drops as we approach 0 or 1. Okay. So this is a softer alternative, remember. So this means I am still saying that my coin is unbiased, but I am now flexible and I can change my belief given you show me some data, right. So I am now flexible and I am willing to change my belief if you show me some data which says otherwise. So this is a softer prior, but it is still kind of leaning towards that the coin is unbiased. At least you are more confident about the coin being unbiased than it being biased or taking some other value. So this you can think of, I do not know, some distribution like this, okay. And the more confident you are before observing data, the variance would reduce, because that means it should, and if you are extremely confident, it will go back to the delta function, and less confident you are, the variance would increase. So this means we have a very important conclusion here. Variance has some relation with our confidence. If you are confident, then the variance would be less. If you are not confident, then the variance would be more, right. So when we later talk about uncertainty, you will realize that we will denote it in terms of variance, not today, but when you go to linear regression and all those things, okay. So variance has some relation with uncertainty, a direct relation with uncertainty, okay. Okay. And by the way, this kind of distribution you can get using beta also. The only thing you have to tune are the A and B, your prior parameters, the hyperparameters of beta to get this kind of distribution. Okay. So, that is also possible. So, anyways, so what I was saying is that for prior modeling, your priors could reflect on your belief, right. Another example is that there is some prior, one type of prior which is known as sparsity promoting prior. Sparsity promoting prior. Okay. Yeah. If it is not symmetric, then you are saying that you believe that the bias is either towards head or towards tail. Now, if that is your belief, that is possible. In that case, it will not be symmetric. That I believe it is unbiased, but if there is a bias, the bias is towards head. Let us say that is the statement, then it should be towards, and so that is possible, but again that should be reflected by your belief. So, it is not necessary to be symmetric, but when I am saying I am believing the coin is unbiased, that means it is neither head nor tail, right. So, I will want it to be symmetric. So, the second thing that we can do with prior, and that is quite common, is known as sparsity promoting prior. So, when do you use it? So, you have theta, right. Theta is your parameter that you want to infer. Now, suppose you have thousands of theta. So, thousands of parameter to infer. Till now we have solved one problem where we had one parameter, but in reality we will see that we might have thousands of parameter. Okay. So, if we have thousands of parameter and suppose our prior belief is that okay, I might have thousands of parameter, but my belief is that many of those parameters would be 0 and only some of those will be non-zero. If that is my belief, then we should use sparsity promoting prior. Okay. Example of sparsity promoting prior, one is student distribution, there is spike and slab, there is horseshoe prior. So, all those examples are there. Okay.
Sir?
Yeah.
So, sir, it means that in this kind of arrangement, the parameters which will be having small values will reduce to 0.
Will give to 0. Yeah. So, that is what it will do. It will encourage parameters going towards 0.
So, only focus on the very important parameters.
Yes, exactly. So, here in sparsity promoting prior, the prior or this type of prior actually pushes most of the parameters towards 0. Okay. Example, one is students the Laplace distribution is also there, that is also a sparsity promoting prior. Laplace spike and slab, this is the most popular probably, and then horseshoe is also there, which is also a sparsity promoting prior. Okay, horseshoe is also there. Horseshoe prior, which is also a sparsity promoting prior. Now, this type of prior, sparsity promoting priors, you will find applications in physical system mostly, because in physical system it has been observed that often only a few parameters actually contribute towards the response. Okay. So, in physical system this kind of priors are used in abundance. Towards the end of this course we will solve one practical, I think the last practical is on equation discovery, where you will see that we will be using sparsity promoting prior, because for equation discovery the idea is that there can be different terms and only few of those are important. So, you will be using sparsity promoting prior. Okay. So, this is the second type of things, right. A third thing as I said earlier, was shift invariance and rotational invariance. So, that is another option. We will not discuss about that, but it is possible. Shift invariant prior. We are not discussing it, but you can study it if you are interested. Any doubt, you can come to me. The other is rotational invariant, also is possible. So, this means that if you rotate it, it does not matter. Those of you who are from mechanics background, you know that there are stress invariants. So, if you are modeling those, this is one example, right. So, and anyways, rotational invariance is everywhere. Then there is something known as, now this is a method, not a prior, but this method is known as hierarchical Bayes. Okay. Hierarchical Bayes, and here the idea is very simple. Remember the problem from last time. So, last time we solved a coin tossing example, and in the coin tossing example, what was the prior? Beta. What were the hyperparameters? A and B. Why can't we have a prior on A and B also? So, if we put a prior on the hyperparameter, then it is known as the hyper prior. In hierarchical Bayes, you also include those priors. You also include the priors on the hyperparameters, and that is known as, then do the inference, and then I will call it hierarchical Bayes. Okay. And a variant or a kind of another alternative is the empirical Bayes, where, and this is where the definition of prior is violated. So, in empirical Bayes, the hyperparameter of the prior is determined based on data. So, that violates the whole prior business, okay, that we are discussing, but it has usefulness, and that is why it is used. Okay. So, the next one is empirical Bayes. It is not a prior, but here the idea is that, and we will talk about this too actually. So, hyperparameters, and hyperparameters, when I say, it means it are these are the parameters associated with the prior, at least in the definition we have used till now. Okay. There are other definitions also. So, hyperparameters associated with prior are determined based on data. And here when I say based on data, so you will be solving a maximum likelihood estimation problem here, but the maximum likelihood estimation problem will not be to find out the parameter, but rather the hyperparameter. Okay. And then again, this is something I mentioned last time slightly, there is non-informative prior. So, what if you do not have any clue? So, in that case you use non-informative prior. Okay. There is Jeffrey's non-informative prior, we will not discuss today, but we might discuss in the next lecture. Okay. So, there is the Jeffrey's non-informative prior, for example, which is a quite popular one. And then the last thing is the thing that we will start discussing now, and is known as the conjugate prior. Okay. What is conjugate prior? It has nothing to do with your prior belief. It is a prior that allows you to do things in an analytical way. So, again we are violating, right, our definition of prior, and we are just selecting a prior for computational convenience, and one such is conjugate prior. Obviously, you can still tune the parameters of your conjugate prior, but still it might violate the prior definition, and conjugate prior is a strong prior, as we will see now. In general, conjugate prior is a strong prior. Okay. You can have strength of conjugate prior, but conjugate prior in general is a strong prior as compared to other priors. Yeah.
What's the difference between hierarchical and empirical?
Okay. In hierarchical, you are assigning a prior to the hyperparameter. So, it is there is a hyper prior. Okay. So, in a hierarchical base I will show you later today that you will see that, for example, last time we had A and B, what a beta distribution. So, I will assume that A and B comes from some distribution. So, that I will call hierarchy because there is a hierarchy now. In empirical I will say that A and B are unknown, let us find A and B by maximizing the data likelihood.
Empirical can be a form of
Empirical can be used
hierarchy.
within hierarchical, but it is not a form of hierarchical, because even in hierarchical you will see that when you go to hierarchical there will be a hyper prior, right, but hyper prior will have its own parameters again. So, at some stage you have to stop, you cannot go on till infinite. It will become clear when you go there towards the end of today's lecture. Okay.
So how will we stop in hierarchy? Like,
You will make a decision. You will decide that why stop now.
so that would be empirical only. Like,
No, it may not be empirical. It may not be empirical. In empirical, you are finding the parameters where you are stopping based on data. You can use hierarchical, but you can decide those data, those parameters without using empirical. So, these things will become clear when you go there, but first let us discuss conjugate. Okay, that is the most important thing actually for the next few lectures. So, okay. So, let me tell you what are the things we are going to discuss in this today and maybe next lecture. We will discuss conjugate prior, definitely, we will start now. We will discuss hierarchical base and empirical base, hopefully today, both. We will discuss at some stage sparsity promoting prior, okay, later, not now. When we go to, when we are done with linear regression and sampling method, after sampling method we will go revisit it, because right now it will make no sense, okay, because you do not know sampling. So, these are the things we are going to discuss. Non-informative I will probably discuss, but with a question mark, let us see. The other things we will not be discussing. So, if you are interested you can study those on your own, but these are the things that we will definitely discuss in this course, starting with the conjugate prior, which we have already discussed somewhat in our previous lecture. Okay. So, let us start with conjugate prior. Conjugate prior. So, based on our previous lecture, can you tell me what is a conjugate prior? What is a conjugate prior based on our previous lecture?
the prior which after using that the posterior distribution is has the same form as that of the
Correct. So, let us try to define it formally, that is, so suppose we have two classes of distribution, and these two classes are P and F. Okay. So, when I say classes of distribution, what does it mean? So, for example, P can be a Gaussian distribution, but a Gaussian distribution is undefined unless I specify the parameters. So, when I say classes, it is like all possible Gaussian distribution comes under P, let us say. All possible binomial distribution can also come under P or under F. So, when I say classes, it means Gaussian distribution with unspecified mean and, so the parameters are not specified, so it is a family, right, but the family term is for something else, so I am not using it now. Okay. Okay, so we are calling it classes of distribution. Now, suppose consider prior pi, let us say, let us use pi for prior over theta given some parameter of the prior, like for the beta it was a and b. So, let us call it eta, okay, and this belongs to P. What does it mean? It is one such, if P is Gaussian, it is some Gaussian with some mean and some variance. Eta is, if it is Gaussian, then mean and variance. If it is beta, then A and B.
pi is
Hyperparameter of the distribution.
pi is some Gaussian distribution.
Pi is in this case belonging to P. If P is Gaussian, then pi is Gaussian. If P is beta, then pi is beta. Okay. So, in our last class the problem we solved, our p was beta and pi was beta with a and b. Okay. So, keep relating with what we have solved in the last lecture, and that was the actual purpose of doing that, so that you can relate it, otherwise it might become abstract, which I did not want. So, that is why that problem was solved last time. Okay. So, consider prior and likelihood if x given theta, and x can be a vector. So, and the likelihood belongs to f. Okay. So, in our last lecture in the coin tossing example, what was capital F? In our coin tossing example, Bernoulli, right? And fx was some Bernoulli with some theta. Okay. So, now with this setup, if probability, I am right, theta given x, okay, x is my data here, remember, belongs to p, then p is a conjugate prior of likelihood f. Okay. So, it does not depend on the parameter of the prior or the parameter on the likelihood, it just depends on this family or the class of distribution. So, for example, for Bernoulli the conjugate prior is beta. For Gaussian with known variance the conjugate prior is Gaussian. For Gaussian with unknown variance and unknown mean the conjugate prior is Gauss inverse gamma, and so on and so forth, okay, or Gauss gamma, I mean if I take it precision. Okay. So, this is the setup. Okay. This is the definition of conjugate prior. Why is it important? It is important because with this setup all you need to care about is what is the parameter of the posterior, and you do not need to worry about finding out the posterior distribution itself. Okay. Because if the posterior distribution now is fixed to be your prior distribution, and all you care about is the parameter of the posterior distribution. Okay. So, with conjugate prior, the computation of posterior reduces to updating the parameters. Okay. Now, remember last time our prior was beta with a and b, our posterior is also beta with a plus nh, b plus nt. So, that means all I had to do was a is equal to a plus nt, that is the updating, right. And even if I getting data one at a time, it will be a equal to a plus n or ni, where you put it inside a for loop, a will get updated for each new data you are getting. Okay. So, that is the usefulness of conjugate prior, that you can now do things analytically, at least the distribution is known, all you need to find out is the updated parameter which corresponds to the posterior, right. And in the last lecture we saw that my prior was beta, posterior was beta, all I had to find out were the parameters of the beta distribution, which was a plus nh and b plus nt. Any question?
So sir, I was thinking that because like in this case, so as we just mentioned that we actually now don't try to figure out the actual distribution, but we fixed it and now just find the parameters.
We do not fix it, because we have selected conjugate prior, it automatically reduces to that.
It uses that, and we just try to find the parameters. And also because this is not the actual distribution that the that value may have, so it is saying like we know that our answer, whatever we get later on, may be different, but it is easier to compute like that.
Right. And that is why it is a strong prior, because by selecting prior you are forcing the posterior to follow a certain distribution. So, if your prior is having so much strength to force your posterior to always follow a given distribution, that is a strong prior. Okay. And that might be wrong, because suppose your distribution was supposed to be multimodal and you select a Gaussian prior. So, your posterior will also be Gaussian. It can never have multiple modes. That is the problem.
Having strong prior is a problem.
Is a problem if your belief is wrong. If your belief is correct, then it is very good. Okay. So, what I was saying is that conjugate prior is a strong prior. Okay. And it is a strong prior because this prior is forcing your posterior to follow a certain distribution. It cannot get changed. It is restricted to that class of distribution. Okay. As it forces the posterior to follow a fixed distribution. Okay. Because it is doing that, it is a strong prior. It is not allowing your distribution to be flexible. It can only be flexible by changing its parameter, but it cannot be more flexible than the parameters allows it to. Okay. So, that is why it is a strong prior. Clear? Now, last time when I said strength, so even in strong it can be who is more stronger, right. So, last time when we were talking about strength, it was about which is more stronger in that sense. But by selecting beta prior, I had already ensured that I am using a strong prior last time. Okay. So, that you should not get confused. Any questions on this? No?
So sir, it's like if we choose a class of priors, those are conjugate priors, then the posterior would always be.
Right, exactly. For example, if your likelihood is Bernoulli, if you choose your prior to be beta, your posterior will always be beta, no matter what data you have, what you do. Okay. So, in that sense. Okay. So, now let me give you one extremely useful property of conjugate prior. Okay. And that is mixture of conjugate prior is also a conjugate prior. And this is very useful because I was giving the example of multimodal. By having mixture of conjugate prior, let us say mixture of Gaussian, you can now have distributions which are multimodal. What does mixture of something means? Let me show you. Okay. So, let us think of, so the key word is this one, right. Mixture of priors or mixture of distribution is the key word actually, priors. So, mixture of distribution. Okay. It means creating a distribution by combining two distributions. Okay, and these two distributions can be from the same family also or same class also. For example, let us say f x x is a distribution and let us say is equal to alpha 1 a Gaussian with x given, let us say mean, right, let us say mean equal to 1, variance equal to 1, okay, plus alpha 2 Gaussian x given mean equal to 10, variance equal to 1. And there is a condition here, alpha 1 plus alpha 2 should be equal to 1, otherwise it will not be normalized. So, alpha 1 plus alpha 2 is equal to 1. You can take alpha 1 to be, I do not know what, 0.5, alpha 2 equal to 0.5, let us take, okay, that is the most simplest one, equal mixing. So, how do you think this distribution will look? Yeah, where will be the modes?
At 1 and 10.
Correct. And then the variance will be there. So, if I plot this distribution, it will be 1 will be at 1, 1 will be at 10, they are equal mixing. So, now remember that this almost will look like 0 because but it will not be 0 because it is Gaussian and these two variants are equal. It's, if they are looking different, it is because of my drawing, but actually they are same because both are 1. Yeah.
So why should alpha 1 plus alpha 2 be equal to 1?
Normalizing. Okay, because that is the property, right. So, okay. Now, obviously, a normal Gaussian distribution is a special case of this. If I take alpha 1 equal to 1, alpha 2 equal to 0, I will get the left one. If I take alpha 1 equal to 0, alpha 2 equal to 1, I will get the right one. If they are close by, they can also overlap. So, this is one example of mixture distribution. Remember, it need not be Gaussian, it can be any distribution. You can also mix a Gaussian with some, let us say, I do not know, some other distribution, that is also possible. Okay. Now, this is clear, what is a mixture distribution? Now, look at the property. Mixture of conjugate prior will also be a conjugate prior, clear? That is the property. For example, if we revisit the example from last time, revisiting the example from last lecture, our probability or the likelihood was equal to Bernoulli, right? Was Bernoulli, I am not writing the parameters again, but it was Bernoulli, right, product of multiple Bernoullis, so a Bernoulli. So, a possible prior could have been 0.5 beta 20, 20 plus 0.5 beta 10, 10. You can also write aka and all those, right. This could also have been a conjugate prior and you could have got a closed form solution. Okay. How I will show it in a while, I will revisit this after I discuss the exponential family, but we will show that how it changes. Okay. Not for exactly this example, we will change the example slightly, but I will show you how it works. Okay. So, the property is again, if you have conjugate prior, you know that beta is the conjugate prior of Bernoulli. So, that means mixture of beta distributions will also be conjugate to Bernoulli. Okay. So, that is the property, that is the statement of the property. Clear?
So what advantage do we get by taking mixture of conjugate priors?
Remember the example I gave you little while ago, that if your actual distribution is multimodal, then without taking mixed, if you are taking a Gaussian prior, your posterior will always be
Have the same as this mixture.
right.
More flexibility.
Yeah. More flexible in some sense, but suppose I use mixture with two components, I cannot get 3 picks.
But we can get 2 or 1.
We can get 2 or 1, right. Okay. So, which means that even in that, with this it is still a strong prior, okay, because you are getting restricted still, but it is more flexible in the sense as you said, right, that you can actually model many things. Okay. But the calculation will become difficult, because for the posterior now you also have to find out alpha 1 and alpha 2, you have to update them. Okay. By the example I have given beta 2020, it is one, I think, that peaks around 0.5, okay, and 1010 is actually towards head. So this is actually that your belief is that, as I was telling to her, right, that my belief is that it is either unbiased, which is dictated by the first prior, or it is biased towards head, in which case it is towards 2. So this is capturing both your belief, because it is not necessary that you will have one belief. Your belief might be, right, that it is either unbiased, or if it is biased, it is biased towards head. So that can be modeled with this, the one I have showed. Okay. Yeah, if you go to the type portion of the slides, which I will go later, the code for this is also given, how you can do this. Okay.
Sir, can you please repeat the last point? I didn't understand.
Yeah. So what I am saying is that beta 2020 is, if you actually kind of an unbiased prior, where it peaks around 0.5, because remember beta is used for theta, theta is the probability of getting head. So beta peaking around 0.5 and being kind of symmetric is like, it is saying that it is an unbiased coin. Beta 1010 peaks around close to 1, 0.8, 0.9, like that, which means it is saying that it is a probability of getting head is more than getting probability of tail, right. Now suppose your belief is that the coin is either unbiased, or if it is biased, the bias is towards head. In that case, what should be your prior? This should be your prior, or something similar, because it encapsulates both the information that you have, both the beliefs. And then once the data is there, if the data shows it is unbiased, then it will automatically swing towards 0.5, the coefficients will increase. And if you see that, obviously the beta parameters will also change, and if you see that, I mean, you will not see, the algorithm will see that from data it is tending towards biasness of head, then the 0.5 of the second beta will increase, and this will change, this 10 and 10 will obviously change anyways. Okay. So that is the idea. So yeah, so this is how you can incorporate both knowledge, okay, if you have both. Clear? So now, can you repeat? Correct, it will. So the second 0.5 will increase, exactly, it will happen, you are right. You are considering both unbiased and biased in this case. So there are three scenarios. One scenario is, I have considered my prior to be a mixture of biased and unbiased, that is what it is. So in that case, if my data is saying that I have got 10 heads in 11 tosses, then automatically the second one will dominate, right. If my coin, I toss it 10 times, I get 5 head, 5 tail, then the first one should dominate. So ultimately your posterior will be a function of your prior and your data, you are correct, right. Okay. So that is the idea. So now the second thing that I mentioned in the title slide was exponential family, and exponential family is important because it is directly related to conjugate prior. So all the conjugate prior and likelihood you will see belongs to exponential family actually, I mean almost all. I don't, at least I don't know any conjugate prior likelihood combination that does not belong to exponential family. Okay. So I will write the statement most, but I think all. most of the conjugate priors belong to exponential family. Okay. Most of the conjugate prior belong to exponential family. Now, what is the exponential family? It is a family of distribution which takes the following form. So, C theta nu x exponential of r theta dot, this is a dot product. So, r theta can be a vector T x. So, if your distribution can be recast into this form, then that distribution belongs to exponential family. Okay. Any distribution that can be recast, that can be arranged and rearranged by mathematical operation and written in this form, then that distribution belongs to the exponential family. Okay. Here T x, this one, it has a name, it is known as sufficient statistics. Okay. So, this means if you know T x, that is enough, you will not need the x. So, from the data if you can compute T x, you are good. Okay. So, this is known as the sufficient statistics of your.
So a sum of two conjugates is also a conjugate, right?
Hmm.
So how does this equation model the sum part?
It can. So there is a proof for that. I will not go into that, but it is possible. Okay. Because it is exponential, right? You will add it up and then join them together. Yeah.
Is it necessary that the functions are variable separable? Like can it be a function like f theta comma x instead of c theta nu x?
It has to be separable. If it is not separable, it is not.
Okay.
It is not. Okay. So, yeah, if it is not separable, it is not. Okay. But remember that something function of x can also be a constant. So, nu x can be equal to very well be equal to 1, and I will just now show you Gaussian distribution, how it comes into this form, and you will realize that for Gaussian nu x will come out to be 1. And this is just one form of the exponential family, there are other forms also. This is the form I like. Okay. You were asking some question?
So if I took a non-conjugate prior because I don't want a strong belief, so how do I convince myself that after some addition or any operations, it will not convert to a conjugate prior?
If you have taken a non-conjugate prior,
Yeah, I take some prior.
then
I believe it was not conjugate,
okay.
but somehow it was made up of conjugate priors. And how do I ensure that this is?
So, if your prior is not a conjugate prior, right, let us start with that. First of all, you will not be able to find the distribution of your posterior. You will have to make do either with the samples from there, or with you will have to assume it to be Gaussian and work with that. So, forget about finding distribution if you are talking about non-conjugate prior. So, that distribution itself you will not be able to find. So, all this finding the distribution of posterior goes out of the picture. So, you, yeah.
Sorry to interrupt. It may happen that after like the posterior distribution becomes a new form of distribution, like it may.
But that you cannot calculate itself. So, you will have only data. Okay. And if it is a non-conjugate, it will never be going to a conjugate prior. So, it will not happen that it will converge and then stay there. Does not work. Okay. But to first of all, you cannot find that distribution. You will have to work with samples in that case for non-conjugate prior. Okay. So, you will not be able to find the distribution there. Okay. And that is why Bayesian inference is so difficult, because if I could find the distribution, then life would have been much simpler, because there is no computational cost. What is the computational cost of writing A equal to A plus NH? 0 almost. Addition is the least possible cost, right? Multiplication has much more cost. b equal to b plus nt. What is the computational cost? Nothing. But I am continuously saying Bayesian is expensive. I am saying because sampling is expensive, and in 99.99% time you have to do either sampling or approximation. Approximation you might not be willing to do, so you will be doing sampling, and if you are doing sampling, that is extremely expensive. Okay. I mean, it's such expensive that it's prohibitive in many cases, and you have no option but to use approximations. So that is the level of computational cost. Okay. So if it is not conjugate prior, there is no analytical solution is not possible. For example, if you use pike and slab prior, there is no analytical solution. If you use student's tree prior, you have to use some numerical schemes. Okay. I mean sampling. Okay. So now examples of distribution belonging to exponential family. Let us write some of those. Bernoulli, and some of these questions will be in your homework, where I will ask you that show that Bernoulli belongs to exponential family. Okay. If Bernoulli is there, binomial will also be there. I am not writing that. Gaussian definitely is there. Beta, and yeah, let us write 3 only, but there are more. Okay. Poisson is one that belongs to this distribution. Okay. So let us just take Gaussian and then see how we can recast Gaussian into this form. Okay. So let us take Gaussian, and for Gaussian we know that f x x is equal to 1 by sigma root 2 pi exponential of minus half x minus mu by sigma whole square, right. This is what we know. So let us see. So we will do some manipulation. So 1 by sigma root 2 pi exponential of, you have minus half, so I will write minus 1 by 2 sigma square, right, minus 1 by 2 sigma square, and then you have x square plus mu square minus 2 x mu, if I open the square and write it in the expanded form, right. And now mu by sigma square, mu square by 2 sigma square, that is a constant. So I want to bring it outside, so I will write it in this form, 1 by sigma root 2 pi exponential of minus mu square by 2 sigma square multiplied by exponential of minus x square by 2 sigma square plus mu x by sigma square, right. And now finally 1 by sigma root 2 pi exponential of minus mu square by 2 sigma square. This I will write as it is. I will multiply by a 1, which I told you earlier also why I am doing that, and then inside the exponential I will write only the parameters in a vector form. So minus 1 by 2 sigma square and mu by sigma square. So minus 1 by 2 sigma square and mu by sigma square. This is a vector. I have already transposed it because it was dot product there. And then the other one is x square and x, right. Okay. So that means this is my c theta, if I am not wrong. What is the notation I used? Yeah, c theta. This is only function of the parameters C theta. This is my nu x. This is my r theta transpose actually, but that is okay. I am writing r theta, and this is my T x. Right? Okay. So, Gaussian distribution belongs to the exponential family, and similarly you can show the others also. You will do that in your homework 1. This will be one question, okay, along with the question I mentioned last time, which was the doing the MLE map and Bayesian estimation for die string example, the Dirichlet example. Okay. So, that is another question. So, I am already telling you what some of the homework problem that will come. Obviously, that is 1% of the problems, but that is okay. Okay, clear? But now one important thing, which is obvious, but let me state it either ways, that do not think that any distribution belonging to the exponential family will be conjugate to every other distribution belonging to the family. It does not work like that. For example, Gaussian is not a conjugate prior for Bernoulli. It is beta that is conjugate prior of Bernoulli. So, if there are two distributions belonging to exponential, there is no need that those two will become automatically conjugate. So, that is not the statement I am making. The statement I am making is that all the conjugate priors that are known, at least to me, belongs to the exponential family, and so is the likelihood. Okay. So, that combination belongs to exponential family, but not that anything. Okay. Exponential family is much broader, that is all I am trying to say. Okay. And the statement is much weaker, do not make it a strong statement. Any question on this one? This derivation is clear, I hope. If it is not clear, make it clear for the homework sake. Okay. Okay. So, now I have 15-20 minutes. So, I do not think I will be able to cover hierarchical and empirical base today. Rather, let me cover the example that I said regarding conjugate prior, okay, mixture of conjugate prior.
Any intuitions as to why exponential families are like conjugate?
If there is a proof, I did it last time, I am not doing it this time. So, one of the intuition is that because of this exponential form, right, when you do the product they become summation. So, it becomes parameter estimation. So, it is because what is the idea? Like you know, right, derivative of exponential is exponential, integration. So, all those things comes with exponential. Similar to when you do the product, it will be exponential of a plus b. So, that will take the same form. So, that is the intuition. I proved it last time, and I showed that what condition is to be satisfied for two distribution in the exponential family to be conjugate prior. So, when you do that calculation, you will realize that it is not always happening, because it has to be separable because of that. Okay. But so that I did last time, I will not do this time, because I will rather like to spend time on the actual part, okay, which is the machine learning using these things. Okay. So, now let us revisit the example. So, suppose we toss a coin n times and obtain n1 heads and n0 tails. Okay. I have tossed the coin several times and obtained n1 heads and n0 tails. If I give you only this information, and this is the only information I am giving you, what is the likelihood? What is the likelihood?
Likelihood distribution beta.
No, that is prior. Likelihood,
हाँ मतलब
probability of D given this thing, right? So, what is the likelihood? Likelihood. What is the likelihood when you toss a coin n number of times and you are only interested in how many heads you have got? Bernoulli
but then
Bernoulli cares about one toss and whether you are getting head or tail. Binomial cares about how many heads you have got. Binomial does not care where the head has occurred. Whether it is the first one or the last one does not matter. So, when I am giving a statement that there are n1 heads and n0 tails, I am not saying that first one is head or tail. First one can be either, second one can be either. So, because of this statement it becomes binomial now. Okay. Instead, if I give you a data where there are n1 heads and n0 tails, but they are at a fixed location, then that will become product of Bernoulli's. So, the important thing here is that by reading the problem statement, you should be able to identify whether the distribution is Bernoulli or binomial, or in general what is the distribution of the likelihood. Because remember, I stated earlier that the distribution or the likelihood is a function of the data generation process and also the experiment you are performing. It is also a function of what you are interested in. Are you interested in each location, or you are interested in, okay, I am happy with n1 heads. If it is happy with n1 heads, no matter where it occurs, then it will become binomial. Clear why it is binomial? It should be binomial, not Bernoulli. So, that is a common confusion, that when it becomes Bernoulli and when it becomes binomial. Because last time also I had n tosses, but I was taking product of Bernoulli. That was because the outcomes were observed and I knew it was head, tail, head, whatever. I could not permute them. In this case I can. Clear? Okay. So, the likelihood is binomial, remember that. I am not writing it, but remember that. So, we consider a mixture of beta prior. So, my P of theta is the same that I mentioned earlier, 0.5 beta 20, plus 0.5 beta 10, 10. Okay. Clear? So, now see if what I am writing is making sense or not. I will call it at probability z equal to 1 and I will call it probability z equal to 2. Is it making sense? Z equal to 1 means the chances of the first component, and that is 0.5 in this case. Z equal to 2 is the chances of observing the second component, and that is also 2 here. Okay. Z is an indicator variable that will indicate that where z equal to 1 indicates the beta 20, z equal to 2 indicates the beta 10. So, it is an indicator variable. Okay, it indicates which of the component. Clear? So, now with this setup, you tell me what will be the posterior. So, I want to find the posterior directly without writing the likelihood or anything, based on what we have done last time. So, can you tell me what will be the posterior look like now? So, forget about the z equal to 1 part, just the beta thing you tell me, what will it look like? What was it last time? But the parameters? A plus NH, B plus NT. Same thing will happen here. So, 20 plus N1, 20 plus N0, 10 plus N1, 10 plus N0. So, from last lecture I am directly writing it. Okay. If it is not clear, see the last lecture. This is quite obvious. So, I am assuming you have studied the last lecture before coming. So, probability of theta is equal to probability of z equal to 1 given d. Why this term is coming? I will discuss that later. Beta 20 plus n1 comma 20 plus n0 plus probability given d beta 10 plus n1 10 plus n0. If I remove the probability part z equal to 1 that one, is everything else making sense? If I am removing probability z equal to 1 part, so with that the beta, the two betas are making sense, because we know that just my prior is my virtual count and it just adds to the count. Last time we saw that. So, when it prior was a and b, it become a plus n h, b plus n t, same thing I am doing here, right. Now, what is the probability part? It is basically previously it was your prior probability z equal to 1. So, it was the prior of your mixing coefficient. Now, it is the posterior, right. So, basically how your belief has updated after observing data. You can, we already have actually in some sense. Here z equal to 1, that 0.5 is the prior, that is the probability in some sense, right. But you can have something more also that you were mentioning, but in this case it is like an indicator variable taking two values. Okay.
So, we are considering distribution for these alpha 1 and alpha 2 as well, and then we are obtaining it using data.
Yes, we are updating our belief using data. Okay. For example, remember what I said, that suppose I perform 10 experiments and I found 5 had 5 del. Then normally my belief about this mixing coefficient should be, it should be the mixing coefficient that is giving me unbiased result.
It should be higher.
Yeah, that one should be higher. It will not be 1, but it should be higher, right. So, that is the what I am saying. So, this is, you can think of it as, so probability z equal to k given d is the updated mixing coefficient. Okay. Now, what is the problem? The problem is I need to find out these two updated value. Without finding this updated value, I cannot evaluate probability of theta given d. So, the main challenge now boils down to finding out probability of z equal to k given d, because if I cannot find that, I cannot do anything else, because that thing is now a function of this. So, the question is how to find probability of z equal to k given d. So, the question is how to compute probability of z equal to k given d.
Z equal to 1 and 2 are mutually exclusive.
Yes. So, k can take 1 or 2, it cannot take 1 and 2. Okay. Right. So, that is what we have to find it out. Now, it is a conditional distribution, right. When we have a conditional distribution, what do we use? What rule do we use when we have a conditional distribution? Bayes rule. Bayes rule. Whenever I ask a question, make an intelligent guess and say Bayes rule. If that is wrong, say sum and product rule. I am sure it is one of these three, the probability is equal to 1. It cannot be anything else. So, whenever I ask, first try Bayes, if not, then either product or sum. The probability of that is 1, this summation. Okay. So, anyways, so probability z equal to k given d is equal to probability z equal to k, this is my prior, right, which is equal to half from my prior distribution. Then, right, some likelihood in some form at least, and then I will write the base rule in the summation form, I mean the denominator in the summation form. So, summation over k prime and z equal to k prime, right. This is the base law, base rule. Now, here probability of z equal to k is something we know, right. Probability z equal to k is known to us prior 0.5 and 0.5 for our example, otherwise also that is known to us. So, what is unknown? Probability of d given z equal to k. So, that is what we have to find out. So, the question now becomes how to find probability of d given z equal to k. Okay. This is what you have to find out. Okay. How will we find it out? So, suppose let us first try to do this thing, or let us write k dash, right, k dash is a generic value. So, probability of let us say theta given d comma z equal to k dash. Can you tell me what will be this value be equal to if k dash is equal to 1? What will be, I hope you have written it down, what will be probability of theta given data comma z is equal to 1? What will be that equal to? Probability of theta given data, the given data is there, correct. So, when z is equal to 1, what is my posterior? Beta 20 plus n1, 20 plus n0, right. When z equal to 2 here, what will be it equal to? 10 plus n1, 10 plus n2, n0. So, basically when z is equal to 1, you should focus on this, and when z is equal to 2, you should focus on this, right. That is what you should focus on. So, you are correct. So, then can I write it as, so this is equal to beta, I have 20. So, instead of 20 was my prior, right, I will write it a k prime. So, I am writing 20 as, or I will write it as a k prime plus n1 comma b k prime plus n0, where a1 is equal to 20, a2 is equal to 10, b1 is equal to 20, b2 is equal to 10. Clear? Right? Now, why did I write this thing? Because I want to use this thing to find out what is unknown. So, that is the reason. Okay. But I do not have time. So, I am out of time today. So, what I will suggest is you try it. Next class, first thing I will do is we will compute this, okay, and I will show you that this comes out to be a function of the normalizing constant. So, next class we will first do this, and then move on to hierarchical base and empirical base. Okay. Yeah.
That is a summation of the two betas, AK dash.
Which one?
The red beta. Is it a summation for A1, B1?
No, there is no summation, because I am saying that my z is equal to k there, k prime. So, I am putting that additional condition there. So, that is why I am selecting, right. If I, so that is the sum law will come into picture if I integrate out z. So, we will start from here, we will prove this thing or find this, and then we will proceed with hierarchical and empirical base next time, and we will solve one problem on empirical base which is related to cancer rate, and we will show you why empirical base is needed, why ML is bad again. So, every class will show why ML is bad, kind of, okay, that is the objective, to show why ML is bad, and we will show that how empirical base probably addresses the challenges associated with MLE. Okay.
So, sir, basically, this base technique is actually much better than ML. The only reason why people are using ML is just because of the cost of sampling. So, if somehow a technique was found which could make this sampling faster, so this would be immediately be used.
This will be used everywhere, and I am expecting quantum to do that, because quantum by default is probabilistic. So, you can sample quickly there, but that is my expectation. Thank you.